Welcome to the afternoon of Madrid, the morning of the US. Welcome to a new activity, a new event at the Foundation, Ramón Areces Foundation. My name is Emilio Golzar. I'm president of the scientific committee of the Foundation, and it is my pleasure to announce to you an event which is a classic among us, which is the 14th edition this year of a relationship that we've had over time to everybody's satisfaction between Springer Nature and the Ramón Areces Foundation to explore the most diverse topics of the scientific world that are of interest. And one of the most interesting today is the sustainability of our planet and the maintenance of the quality of the air we breathe. And we're talking about not just producing less CO2, but trying to absorb or collect or capture part of the excess CO2 we've produced. So it's an honor and a satisfaction to welcome our colleagues, Spanish and North American colleagues, to Springer Nature, and I will pass the floor without further ado to Soledad Santos, editorial manager for Springer Nature for Spain and Portugal.
Erika Pastrana. Ahora es Soledad, ¿vale?
Welcome to the 14th edition of this meeting, which is the result of a collaboration between the Ramón Areces Foundation and Springer Nature. For the second year, this is done online, and we hope and expect that the pandemic goes away little by little, and that next year we are here in person and we have a fascinated audience with us. Throughout the pandemic, we've learned that the global problems require global solutions. The topic this year is the capture of atmospheric CO2 technologies for a sustainable future brings us close to a world problem, which is global warming. It is obvious that the increased population and the growing demands for water and energy make it difficult to achieve the sustainable development objective of the UN. But we believe that collaboration between scientists, governments and the population can help us to develop and apply strategies that bring us close to that objective, to that goal. One of the most important measures is the reduction of emissions of warming gases and the increase of renewable energies. This measure is important, but won't be enough. We will have to use other technologies and methods that help us to reduce greenhouse gases and carbon dioxide in particular. We'll hear our speakers tell us today about the most recent advances in the strategies for CO2 capture, storing of CO2 in geological structures or the oceans, and the design of specific materials for capture and transformation of CO2. At Springer Nature, we are firmly convinced about the importance of disseminating the most recent scientific advances so that they reach the public, and promoting conversations between academic scientists, the private industry and governments. It's essential for all of us to set up a conversation that allows us to introduce efficient, feasible measures that contribute to a more sustainable future for us all. And to show you our commitment, at Springer Nature we have participated at the Glasgow Climate Summit, COP26, and also in the organisation of the second scientific conference for a sustainable future organised by the UN, and we have incorporated into our portfolio magazines, publications and books that are focused on sustainability. Like every year, we thank the Foundation, Ramón Areces Foundation, for giving us the opportunity to be here, and we thank its scientific committee and its representatives for choosing such an important topic that it's so necessary to discuss, and we hope to inform the public about one of the most threatening problems we face today. And we thank the General Director of the Foundation, Mr. Raimundo Pérez, Mr. Manuel Azcona, Director of Communication, for their trust and for helping us to organize these meetings even in times of pandemic. I would also like to thank our speakers, Jorge Rodríguez, Ah-Hyung, Jorge Rodríguez, Jean-Paul Lange, and Rosalind Rickaby for participating in this meeting. I hope you enjoy it as much as we will. And I want to thank Erika Pastrana from Nature Research for being with us. We hope to have you here next year in person. Thank you very much to everyone and enjoy the presentations. Good afternoon, everyone. I would like to also thank the Ramón Areces Foundation for continuing to support science in all its aspects and also for helping us at this time to disseminate topics of social importance and have experts with us to talk about these things. As we have said, global warming is one of the most threatening problems we face as society in the 21st century, and it is one of the topics that requires urgent measures. In 2015, international bodies got together in Paris to agree on urgent measures to reduce CO2 emissions into the atmosphere and also transform the energy production to renewable energies. These measures were aimed at trying to reduce global warming, and the aim was to not increase the temperature of the planet more than 1.5 degrees. 7 years later, as we have just heard, we have had another climate summit in November in Glasgow, and the prognosis is more pessimistic. Some experts estimate that by 2100 the temperature of the planet could have increased by 2.5 degrees, which would have catastrophic consequences. To reduce climate change, it is necessary to reduce CO2 emissions and also turn our energies into renewable energies. But those measures alone will not allow us to achieve that goal. We must also resort to science, technology, engineering in order to develop and implement measures that allow us actively to capture and reduce emissions that have to do with human activities, CO2, anthropogenic CO2. And it is this topic that we're going to talk about today. We have 4 international experts that are going to talk about the different techniques for capturing, using and storing CO2. We will talk about, as my colleague has said, methods to capture CO2 with geological structures, the role that different elements might play here, and the design of new materials to capture CO2 or new fuels that will allow us to replace fossil fuels. To give you an idea, these strategies, which in English are called carbon capture, use and storage, are being implemented in some industries, factories that produce great amounts of CO2, the steel, cement industry. Some factories in the world are already using devices to capture part of the CO2 they emit. But throughout the year, or at this time, we only capture about 40 million metric tons of CO2, and our ambition to control climate change would require us to increase that capture by more than 100 million times. I hope you understand the importance of this issue and that you are thankful that we are going to spend this hour talking about the scientific methods that will allow us to achieve that goal that is of interest to us all. And I invite you to stay for the debate. I will ask and I will chair that debate and ask questions, and we'll have questions and answers from these experts. But without further ado, I would like to pass the floor to the first of our speakers, Dr. Alissa Park, who's director of the Lenfest Center for Sustainable Energy, and she's the head of the Earth and Environmental Engineering Department at Columbia University in New York. She's going to give us a global vision of the measures required to address the circular economy of carbon. Alissa will also talk about her research into on-site carbon capture. Thank you very much, and I'll pass the floor to Dr. Park.
Thank you very much, Erika. You actually covered quite a good ground, which is wonderful. So I'm really great to be here, although it's a virtual, and Spain is a wonderful country, so I'd love to visit again sometime soon. Today, I would like to give you some overview on what does it mean by carbon capture, utilization, and storage. And hopefully you'll get the reason why we need to work on it and what we need to focus next 10 years, 50 years, or even 100 years down the road. As Erika mentioned, this is the global problem. We are not only talking about carbon management, we are talking about climate change mitigation or climate change issues. And as she mentioned at COP21, which was 2015, entire world got together and said, this is the big issue. This is something we need to work together on. And that's why they came up with these mission innovation challenges. And this is quite interesting because in my mind that this was almost the first time entire world got together and said that not only we need to deploy technology we already have, but this bridge to the sustainable future is so long that we need to really push fundamental science and engineering at the same time. Because when you're thinking about it, any technology to be deployed, it takes about 2 decades, which means that the technology we'll be using in 2050 or 2100, we do not have it yet. So we need to work on both fundamental research as well as commercialization of the technology we have today. So during the meeting, people discussed what are the important aspects or what are the areas we really need to focus our emphasis. And if you look at these buckets they created, there are 7 different buckets they came up with first, and now they added one more a year later. So I guess you can recognize things like a sustainable biofuel, I think we'll hear about. There's converting sunlight and hydrogen. But you also see there's carbon capture, utilization, and storage. Basically, you're saying that we have so much emission of CO2 already and historically emitted, so that we need to deal with carbon actively while working on many other technologies. And another important key point is these are not siloed topic areas. All these thrusts are interconnected. So looking at the holistic view of how to address as a whole instead of focusing on one single solution is really key for the future. So looking at that, United States, we have changed our direction drastically this year and last year. So last year with the new government, Secretary of Energy started thinking that, okay, we are really committed, but without resources and support, we won't get there. So there are something they started, it's called Energy Earthshot Initiative. This is amazing because they're saying, regardless the cost, we'll get there. Similar to moonshot, like how we want to go to the moon. Now we are committed so much. The first Energy Earthshot was about hydrogen. And it's all about net zero economy by 2050. And the goal is we want to make $1 per kilogram of hydrogen in 1 decade. This is really ambitious goal. And this was announced last June. The second one was announced is this one. Let's see, we can go to the next one. Okay, there we go. So second one was announced in early November last year, which is only a couple of months ago. It was about carbon negative Earthshot. The goal is less than $100 per ton of net CO2 by 2050. This is including the carbon capture, utilization, and storage, and they're trying to create the creative, innovative pathways to get there by 2050. Again, very ambitious goal. But because of this, there's a lot more push in both fundamental research and higher TR research at this time in the United States, and hopefully that will have a lot more international collaboration in these areas. So let's think about what is the carbon capture. These are some of the technologies, there are many of them, to capture CO2 from a wide range of concentration streams. And you'll hear about the unique materials like the metal organic framework later on in this session. And many of the materials capture CO2 chemically, for example, like amine-based liquid solvents, they're doing actually catch and release. because you don't want to use the material only once and throw it away. That doesn't make any sense because all the materials has its own carbon footprint. So when you develop the new technologies, you need to be able to use these materials in thousands and thousands cycles. So the question became, the material captures CO2 very effectively, will require a lot more energy to release that CO2 back into CO2 form. So then people were looking for what is optimum binding energy so that it is decent enough to capture CO2, but it's not too much energy penalty to release that CO2 back. So after studying all these, and also you want to do all these reactions super fast because the rate of the reaction determines what size of reactor we need to develop. There are some good candidates, including monoethanolamines and many different amine solutions. And this liquid solvent is very easy to move around between reactors, and they were able to actually develop into large-scale demonstration. So this is one of the first large-scale demonstration in the United States. We started late 2016. We call it Petronova project in near Houston area. I think many of the speakers are very familiar with. We were capturing more than 1 million tons of CO2 captured. There were some challenges because these materials do degrade over the time. So we have to learn a lot more about how to scale up these technologies because amount of carbon we have to capture is tremendously large. So we are learning a lot more on this, but at the same time, there are other novel materials we've been working on. For example, I think it takes a while to go to the next slide. Okay, here you go. So what would you do once you capture CO2? That's a big question, because as you just saw in the photo, the amount of carbon dioxide we're going to capture is a huge amount of volume. If you really care about the climate change, we cannot use up all this CO2 and put it into work because the amount is so much, way beyond the carbon we can absorb into the chemical and materials and fuels sectors at this time. So we actually do need to store in geological formations or even in the ocean, which you're going to hear about later on. So we found a lot of these pockets, almost like a storage tank underground and different void spaces we can put our carbon dioxide once it's captured. In order to inject this CO2 underground, you have to usually compress this CO2 up to 150 atmospheric pressure. You want it to be very pure so that you can inject efficiently with the maximum amount of CO2 being stored. And if you look at the right-hand side figure, which is famous Sally Benson's figure, there are different modes it goes through once you inject CO2 into these reservoirs. Sometimes, initially, they're trapped under the cap rock, but afterwards, they start to go into the pores. And ultimately, only if this reservoir has reactive rocks, you can even do mineral trapping. Then mineral trapping is quite interesting, which I'm going to talk about it later a little bit too, that this is one of the very few pathways you can go downhill in thermodynamic energy level. So from the coal or natural gas or any of the carbon-used fuels, you combust or use it and become carbon dioxide. It's a very thermodynamically stable material, and that's one of the reasons we have a hard time reactivating them, making chemicals and fuels. But you can do reaction with these materials, with alkaline materials, and make solid carbonates. And it's really interesting because if you can solidify this carbon in geological formations, maybe we don't have leakage issues or risk of the mobility of these high pressure CO2. But as you can see in the bottom right figure, there's no number in the time scale. Because at the beginning, we really had no idea how long these reactions or different trapping mechanisms will go through. One of the really interesting research happened in Iceland is called CARPEX project. Now there's a second phase of it. In the geothermal side, they were able to inject large amount of CO2 into these basalt reservoirs and rock formations. And they found within 2 years, they start to see solid carbonate formation. As you can see in the photo on the right-hand side, bottom right, these white crystals are solid carbonates. The CO2 we capture either directly from air or from the power plant, we can actually inject into these formations and solidify them. Having said that, if you look at the left-hand side figure, which is the data from or estimates from McKinsey published in 2020, in mid-2020, they said the potential in 2030 for carbon storage is light gray bubble. This is not insignificant, and hopefully this is the underestimation. Hopefully we'll do a lot more than this. But you also see these black bubbles right here. And this is what they estimated as carbon utilization potential. If you look at the bottom right photos, this is quite interesting. It's the city of New York. Hopefully one day we can also have a meeting here. And if you look here and also the bottom figure, there are a lot of materials in there to build a city, to have consumer products, or look around your room. It'll be very hard for you to find any material without carbon in it. So when we talk about decarbonization of power sector, we should get there by doing a lot of renewable energy. But can we decarbonize the chemicals and materials? No, because carbon is an essential building block for all these materials and chemicals. The question is, can we rebuild the entire ecosystem of the industries producing chemicals and materials without fossil carbon? So I call it defossilization, and that's the key. So let's look at how we can do this. So we know that our society needs chemicals, materials, and fuels. And consumers need it. We need to sustain our lifestyle and our society, supporting everyone. And eventually these will go into waste streams. It could be into air, it could be in the water stream or solid stream. Can we have this nice new bubble of a new circular carbon economy, and only input should be renewable energy and hydrogen with the lowest carbon footprint or zero carbon footprint? Then we can capture CO2 reacting with these hydrogen with the renewable energy. And then we need to create tech to market pathways so that we can have a circular economy. But at the same time, this is not going to be happening unless we have good economics and policy and regulatory framework. So this is a big challenge. And as you can imagine, a lot of these chemicals and materials and fuels go across the boundary of continents and countries, imports and exports. It's not a really easy solution and big challenge. But very interesting way, we really need to frame our future direction for not only energy side, but material side for the future. So let's talk about where to get carbon. Because as I told you that we want to use non-fossil carbon. Ultimately, if we're going to stop using non-fossil carbon to build entire ecosystem of industries, there are only a few options, in my opinion. So there's air, there's ocean, there's a lot of carbon in there. We can get them directly from ocean or air, which you're going to hear about it later on. But also you can go through biological pathway, either terrestrial or marine biomass. These are some of the options. There are challenges and opportunities for each of the pathways. Today, I'd like to tell you a little bit more about the direct air capture. And direct air capture is interesting because similar to our trees, but we are doing chemically. This technology, compared to point source capture of carbon dioxide, they moved a lot faster in their development. They still have a lot of big challenges. But the reason is, as you saw the photo I showed you in the Petronova project, which is a huge in scale, industrial scale, somehow or another, direct air capture technology is always being developed as a modular design, which means that instead of scaling up, which is much harder to do in short time frame, they're doing copy and paste, which is scale out. So they were able to learn from their own mistakes very quickly. And this is the photograph in Switzerland, how they do direct air capture by the Climeworks, one of the big startup company doing great work at this time. Capturing carbon dioxide from air versus point source is very different. In a sense, challenges are different because the point source, usually CO2 concentration is really high, but direct air capture, you're dealing with only 400 ppm CO2, which is very low in concentration. So capturing CO2 from 400 ppm all the way to 90-95% capture is really, really bigger thing to do. So the target is usually 60+ CO2 capture directly from air. But there are other challenges really specific to direct air capture. You need to process so much air to capture a little bit of a very tiny concentration of CO2, means that you cannot afford to have a high pressure drop because you cannot compress that large amount of air to go through your direct air capture systems. Also, in air, unlike in the power plant, you have a very high concentration of oxygen. So oxidative degradation will be a big challenge. And every day we have different weather systems so that there'll be a fluctuating humidity and other temperatures and other environmental conditions. So these are big challenges, but also there are a lot of opportunities for direct air capture, which doesn't need to be co-located with power plants. So in terms of direct air capture materials, people looked at many different things. And here are some of the really more novel, innovative materials still in the fundamental level. I'm not going to go through too much chemistry. There's ionic liquid, cobalts, and the material I'm working with, which is called NOMS, which is nanoparticle organic hybrid materials. All these materials are unique, especially ionic liquid and NOMS, because it does not have vapor pressure. Means that it looks like a honey-like material, and you can leave it outside environment for days and weeks and months, and it won't evaporate. Unlike an amine-based solvent we talked about for point source capture, if you leave it outside, water will evaporate and you will not have solvent anymore. But this has a very unique property so that you can leave it outside without worrying about evaporation of solvent materials. But the challenge is these materials are very sticky and high in viscosity. So first thing we looked at was, does it capture CO2 very well? It does. So we compare it with the amine-based liquid solvents, and we can even do better than that by decorating all these polymers with amine-based materials. But as I told you, the challenge is how high this viscosity of these liquid materials are. So if you leave the honey outside, you have all the dust being collected on the honey, and as well as it's hard to move them around. So people start thinking about how to innovatively create the way that this material can be moved around in different reactors, capture reactor, regeneration reactor, without mass issues of transportation, as well as improve the mass transfer so that we can overcome the high viscosity issues. There are many different ways to do it, but what we decided to do is encapsulation. So basically, this very high viscous solution of liquid, if we can chop them apart and then package them apart, maybe we don't need to worry about all these high viscosity challenges. So these are some of the examples of encapsulated solvents. So blue colored liquid is NOMS, and we can actually create a lot of interface areas for gas capture, which is the CO2 capture into these materials. And by doing so, the comparison of how fast CO2 can be absorbed by these materials is tremendously faster. As you can see, the red colored data is when you have neat NOMS, and as we encapsulate them, we have orders of magnitude faster uptake rate. We start also thinking about how about other modes of encapsulating these materials. So even to further reduce the pressure drop, we start to thinking about fiber encapsulated CO2 capture materials. We can still start with the NOMS, which is really excellent at capturing CO2. Working with Michelle Kidder at Oak Ridge National Lab and Young-Ju at Cornell University, we started to blending or combining, assembling these two materials. NOMS capturing CO2, pure material has really high porosity as a shell material for these electrospun fibers. Now we can envision that these fibers can be made as like a filter system in your furnace. Very low pressure drop, which we use it all the time. Now we can put this filter system outside in the wind to capture CO2. And as we expected, it does a great job in capturing CO2 much faster compared to neat NOMS. We had a currently 25-fold increase, but we are continuing to improve these fibers to capture CO2 directly from air. And we also implement this technology in the buildings to capture CO2. So once you capture CO2, what would you do? As I mentioned, if you really care about climate change mitigation, you have to store. But at the same time, we don't want to wait until we draw down all the CO2 to start thinking about CO2 utilization and circular carbon economy. So a lot of fundamental research is going on at both academics and industrial level, and this is what people are thinking about. This is a DOE's list of the things you can make if you have carbon dioxide. And when you look at the center, there's captured carbon dioxide. Until now, more of us in the carbon capture area was told that we're going to store this CO2, which means that you have to get the pure CO2 dehumidified, pipeline-ready, high-pressure CO2 at 150 bar. But this is only when you try to link capture to storage. But if you decide, I'm going to capture CO2, but I'm going to do something else, I'm going to make different products shown here, then maybe you don't need 150 atmospheric pressure. Maybe you don't need to be high purity CO2 either. So that opens a lot of interesting avenue to really reduce the price of carbon capture, because our compression cost, the purity of CO2 really increase the need for high cost of carbon capture. So we started looking into a lot of these. First, the reason we did not work on this area is because we did not have carbon-free energy. As I showed you in the energy diagram, carbon dioxide is in low energy, so that you really need to get carbon-free energy to push that back up. But as you heard recently, the deployment of renewable energy is a lot faster than we expected. Really nice surprise. And sometimes we even have negative price of electricity in California in the United States. Can we utilize these niche markets to really study or deploy our ideas so that we can create this circular carbon economy? In order to do that, you need better sustainable catalyst, earth abundant catalyst, or something effective catalyst. A lot of research is going into that area. But as you saw in the bubble I showed you, the input is not only renewable energy, but hydrogen, because carbon dioxide has only carbon and oxygen. So in order to make chemicals and materials, we need hydrogen as well. So in order for that fuel or products and materials you made to be sustainable or even carbon neutral and so on, you need to make sure that your co-reactant, usually hydrogen, has to be sustainable as well. Some of you may have heard hydrogen now have many different colors. There is a black, gray, blue, green, and all these color kind of indicates that what is its carbon intensity. I'm not going to be able to go through that today, but then basically we want to get hydrogen with the lowest carbon intensity for this whole idea of CO2 utilization. So idea is, instead of focusing on only carbon capture from point source, let's look at the wide range of sources. We can look at the power plant, but also ambient air or cement industry, steel industry. And the question is how to grab those CO2 and deliver to the surface of the catalyst. It could be electrochemical conversion or thermal conversion in many different modes. Can we effectively deliver and activate to make all these chemicals and materials which we can circulate? Again, input should be only renewable energy and hydrogen with low carbon intensity. The last one I want to touch upon just briefly is the carbonate pathway. As I discussed in the energy level, carbonate is the lowest energy level. So this is one of the few CO2 conversion pathways, energy downhill. It does not mean we can do it easily because there's a large activation energy. But it becomes quite interesting question because if you look at this figure, what material I can react CO2 with to make solid carbonate? There are a lot of natural materials, but also a lot of industrial materials. So if you look at the blue plot bars here, there's a fly ash from power plant, steel slag from iron and steel industry, and red mud from the aluminum smelting plants. Interesting thing is these alkaline solid waste co-locate with CO2 point sources. So we can have one waste, which is solid, another waste, which is gaseous. By doing acid-base reaction, we can create another material for the new market, which is quite interesting. So there's a multifaceted environmental benefits. So this is one of the technologies developed at Columbia University. If you look at the top figure, on the left-hand side is how we used to do iron and steel production. There's a lot of flue gas generated with CO2 and other gaseous pollutant. There's a lot of waste heat and solid waste with a lot of calcium and magnesium. We looked at it as not a waste. Maybe we can see this as unconventional resources. Why not? So if you look at the right-hand side, we proposed is that using CO2 from flue gas, using waste heat, and using slag has a lot of calcium and magnesium, we were able to make carbonates for paper fillers, construction materials, plastic fillers. At the same time, we recover iron oxide and other critical elements out of these systems. This technology, we've been working on it about 10 years, a little over 10 years, and I'm happy to tell you that it's being commercialized in China at this time in Baotou scale, in commercial scale this year. So hopefully we'll go to the next slide. Give me 1 second. Okay, so I'd like to summarize with that we need to consider all CO2 sources and multifaceted solutions because there's no one solution can solve entire carbon management issues. CO2 conversion and utilization for the first time now start to play an important role because of the renewable energy become very affordable. Reactive separation, systems engineering, and understanding how to do life cycle analysis correctly is really important to really understand what is the net impact of these new pathways. We can consider new pathways to existing chemicals, but why not develop new pathways to new chemicals? But most importantly, all this has to be done putting environment within our system boundary. Thank you very much, and I'll be happy to answer any questions during the debate. Thank you.
Thank you very much for this presentation. So I would like to give the floor to the next speaker today, Dr. Jorge Rodríguez Navarro. Dr. Navarro is Professor of in Organic Chemistry at the Granada University. His research group has been working in recent years in strategies for capture of CO2 based on its physical and chemical characteristics and in the use of solid adsorbents and also the advantages that this may mean against the aminated solutions we have just been hearing about. Dr. Navarro will talk about the last progress in material engineering designed for CO2 capture, and he will also cover the potential that technologies as the big data or AI can have for the design of these materials. Thank you very much, Jorge. Esto no lo toco yo. Good afternoon. It's a pleasure to be in this seminar and to be able to talk, and I thank you for the opportunity that both the Ramón Areces Foundation has given me and also the Springer Nature Group. I'm going to start sharing my presentation. Well, as Erika said, I'm going to talk about the possible use of metal-organic networks in the capturing of greenhouse gases. My talk will be structured based on a brief introduction. As Dr. Alissa said before, on the problem of climate change, the strategies for capturing CO2 based on its physical and chemical characteristics. I'm going to talk about the advantage of solid adsorbents against the current technology, capturing CO2 in aminated solutions. And then I'm going to talk about the steps used for the design, synthesis and modification of metal-organic networks for the capture of gases, greenhouse gases. And finally, I'm going to talk about big data as well in the accelerated search of better materials for capturing CO2. As the previous speaker has already told us, at present we are facing a series of abnormalities in the Earth's temperature, and that since the decade of the 80s, last century, this has been accelerating. And this is attributed to the known greenhouse effect that we believe is responsible for that climate change that entails the problem that the temperature will have reach very high level of temperatures and hurricanes and other problems. The origin of that so-called greenhouse effect is due to the fact that the Earth is subject to a strong solar radiation, and when it reaches the surface of the Earth, it becomes a radiation of a greater wavelength. In turn, this is absorbed by gases that are present in the atmosphere that are known as greenhouse gases. A beneficial effect of the greenhouse effect that it maintains a stable temperature on the Earth that makes it possible to live in it. But on the other hand, there are subtle changes in the energy balance. Sun-Earth can have dramatic consequences for the climate. And this is something that we are experiencing right now with the so-called global warming. But we could also be facing in the future a glacial area. The greenhouse effect is due to the fact that there are present problems in the atmosphere that are able to absorb very strongly this infrared radiation, due to the fact that those molecules induce vibrations, and they give rise to the absorption of the infrared. We have reflected in this picture what is this infrared spectrum of the air, and we can see that there is a very important contribution of water and also of CO2. But nevertheless, we believe that the greenhouse effect or its abnormality in the energy balance are caused fundamentally by the increase of concentration of gases that cannot be condensed, particularly CO2, methane, and nitrogen oxide. The origin of those gases has been reflected before. It comes from the enormous consumption of fossil fuels in order to maintain the energy requirements of our society. And as we can see, this exaggerated consumption has given rise to a significant increase in recent years of the CO2 concentrations, and thus that increase of the greenhouse effect. We know that the fundamental problem is due to the presence of growing amounts of CO2. So we are going to say a few strategies that we could approach in order to capture CO2 based on the characteristics of this gas. Some things have already been mentioned by Dr. Alissa Park. For instance, it's an acid molecule, so if we treat it with a base, we are going to be able to capture it. And this is something that has been done. The muscles can construct bivalves. And another property of that molecule that is also useful is its electrophilic nature. Both if we postpone it to an amide that has an electrophilic nature, it's going to give rise to the action of chemical compounds that are the carbamates that are able to filter it, the CO2. Or if it's an oxide, we could think about a reductor that could fix it. And this is something that nature does already very well with the plants. And finally, another feature that we can use as well is consider the size of the CO2 molecule that has been mentioned, a very, very small molecule, and we can think about confining it in reduced spaces, and this would be a porous material. Of course, we can also consider different combinations of all these types of interactions. Here we describe the current technology, also mentioned by Dr. Alissa Park before, where you can see the attack of the amine group or force on CO2 to give rise to this carbamate. The process of capture is a good one, as we have heard before, but it entails a very high penalty when we have to revert, to regenerate the adsorbent and free CO2. It has a strong penalization in energy and economy in a power plant. And this entails, it leads to beta-amines, that has been mentioned before, and it's not too adequate for the direct capture of CO2 from the air. So I would like to point out that we can go from the capture of CO2 in gases with a solvent and go over to the capture of CO2 in a surface, in a solid surface. How can this be done? It can improve the capacity of capturing that gas, increasing the surface. Here we have the case of a place where you hang your clothes, where what we have a system that has a lot of surface that allows us to have a rapid exchange with the air and allows the drying of the clothes. Or similarly, in a porous solid frame, we have a lot of surface in a condensed manner or tight manner, where we could maximize the capture of these gases. This can be obtained with different materials, but I'm going to focus mainly on a type of material that is synthetic, that are metal-organic networks, that are porous, that are based on inorganic fragments, normally metal fragments, and an organic spacer, that when they are linked between them, they give rise to a structure and they give place to channels and cavities and holes where different processes of molecular recognition may take place. An advantage of this system, of this type of, is that its design per se is relatively simple. It's just based on choosing or selecting pieces of construction that are adequate and put them together, assemble them together. It's a type LEGO or interaction. And the peculiarity of these materials is that they may reach having specific surfaces that are very big, very large. 1 gram, for instance, of one of these materials can have the surface of a football stadium. In this case, there's the Granada football stadium. People like it very much. I don't like so much football, so it's not. But not everybody agrees with me. Well, and as I said, the advantage, as these are modular materials, and they are and we combine inorganic and organic fragments. This example, selecting a variety of organic spacers, we are able to control in a very precise manner the size of those cavities or those holes. This is what we've done in work in my research group, controlling the size of the spacers. We can control the size of the cavities as well, of the holes, in order to homogenize them for capturing of CO2. The CO2 capture is considered the adequate pore size for this molecule is around 3 times the molecular dimension. Bearing in mind the dimensions of the CO2 molecule, we are considering that a pore around 1 nanometer would be adequate in order to allow the diffusion and the adequate interactions, giving rise to a reversible interaction. This is something that has already mentioned before, and it's important both for the capture and the later release of that CO2 molecule. Likewise, this type of systems allow functionalization with different polar groups that allow for interaction with the quadrupolar molecule of CO2. An advantage of these materials is that they are crystalline systems, and this means that they are made of holes and channels that repeat in a monotonic fashion in the three directions in space. And this makes that they give rise to selective interactions with the molecule that are able to discriminate the size of the different molecules. And this gives them properties that are known as a molecular screen or sieve. This is a crystal, a real one, and it's repeated homogeneously. And this gives rise to implementations. But the reality that we find is that these crystals of this material, and generally all solids, are not perfect crystals. They do have imperfections. It's known as defects, dislocations, specific defects, or even large-scale defects. These defects are favored thermodynamically, and those makes those materials more vulnerable. It's important also to point out that many of the properties associated to these solids is linked with the presence. Well, we can say what colleague Humphrey said, that the defects, like in people, makes that the porous solids are interesting. And this is something that a group of researchers has exploited very much in what is the generation of defects in order to improve the properties of those materials. One of the goals was the CO2 capture. But here we can see that the treatment of one of those systems with alcoholic protease or glycolic gives rise to gains to the incorporation and also implement of elasticity in these modules, in these fragments, metal fragments. This gives rise to the creation of highways with these favoring more the CO2, and there are improved reactions with those basic centers or these centers where there is polarization. All this gives rise to a significant increase in the capacity of absorption of these materials, selective of CO2, comparing with the defective materials. We have only been able to show this. We have been able to show this by means of measuring different curves in which gas flow goes through, simulating in this case the combustion of the gas issued by a central power station, where the defective material is able to retain during more than 30 minutes selectively the CO2. This improvement in the capacity of adsorption is due to two factors. We create basic centers, nucleotidic, and are able to attack the CO2 molecule, giving rise to carbonate, and this interaction or the formation of this fragment is totally reversible. Another advantage of these materials is that they can be, we can fine-tune their properties by means of ion changes, and different ion changes in order to make that the interaction with another type of molecule, SO2 I think he said, is more effective. And in this case we can see that adsorb and regenerate multiple times without any loss of adsorption capacity. So these are totally reversible interactions. I'm going to leave the defects and I'm going to focus on what we have told about the big data before. I just said a few words about it. We have collaborated in a virtual work in the search of new materials for CO2 capture that is similar to what is the selection of drugs based on the natural dose. In the search for drugs, we know a protein that is responsible for a disease. We know its structure and thus the structure of the active center of that protein. So what it's all about here is to look for a molecule that adjusts, fits with the model of interaction that adjusts with the keyhole or the center of that protein and blocks the activity that causes the disease. So we can create a big, important library that can be made out of known compounds and also the use of unknown compounds. We have a computational screening, and we can see the type of molecules that fit better to that center. And once we have selected those molecules, what it's all about in a later phase is to bring it to a clinical trial to see if it works, if there are toxicity problems, etc. In a similar way, in the case of the search of better material for CO2 capture, we had the reverse situation. We know the ligand, what would be the drug, but we don't know the structure of the host molecule, what would be what we know, what we call the adsorbaphore. Adsorbaphore. We have built a library of structures in this case with potential capacity to capture CO2. We have made a screening, computational screening, and until we found a molecule with material that is able to act selectively on this molecule, what we call the adsorbaphore. And once we find this adsorbaphore, what it's all about is to reach a validation, experimental validation of that system, to find the active center. In order to do that, we have built a virtual library of more than 300,000 MOFs, and we have explored their different properties by means of data mining in order to find a material that has a high capacity and selectivity for the absorption of CO2 against nitrogen and water. These are compounds that will be most in the air or in the gas in a power station. So the striking thing here is that we have found that the structural motif, what is called as adsorbaphore, the ideal one, are two aromatic rings separated by 7 Armstrong, where we can adapt the CO2 molecule as a sandwich, so to speak. And finally, the last step of the study consisted in synthesizing in a guided manner one of these materials and validate the properties of capturing CO2 at the experimental level. And with this, I conclude my talk and simply point out that this type of materials are adequate for the optimum capture of CO2, and that apart from the synthesis of MOFs, it's interesting to see the defects, and or I have shown some examples of the possibility of big data when we discover materials in an accelerated manner with good properties. Finally, I would like to thank my research group in the Granada University and the international collaborations. And thank you very much to all of you for your attention. Thank you. Thank you, Jorge, for this fantastic presentation. And now I would like to introduce the third speaker this afternoon and give the floor to Dr. Jean-Paul Lange. Dr. Lange is the main researcher of Shell Projects and Technology in Amsterdam, Netherlands, and he's also professor of Engineering, Twente University in Netherlands. Dr. Lange has worked on fossil fuels and in recycling of plastic waste. In his talk, we are going to listen to how we'll talk about the potential of the biomass to replace solid fuels and as a source to producing new chemical compounds and be an alternative to fossil fuels. Without further ado, I would like to introduce Dr. Jean-Paul Lange.
So the question following up of the lecture from Alissa and from Jorge will be how can we defossilize today's society, get rid of the fossil hydrocarbon that we are using, switch all our energy to renewable carbon lean energy, but also looking at the materials that we are using and making sure that those materials are also carbon neutral. So let's look at where we use those hydrocarbons for. In terms of energy, we will use them for powering industry, transport and building sectors, either by producing electricity from fossil fuel or by directly burning the fuels into those sectors. And we'll also need fossil hydrocarbons for making chemicals. Now, a part of this sector can switch to renewable electricity, but another part will be more challenged in doing so. For example, building can switch quite largely to electricity, renewable electricity, but industry and transport will have much more difficulties in doing so, as we can see, according to Shell scenarios, up to the end of this century, scenarios that are developed to meet the Paris Agreement of limiting the temperature rise to 1.5 degrees Celsius. We could have by the end of the century about half of those sectors being supplied by renewable energy, but still half of it being supplied by fuel for heavy duty transport like aviation, or heavy duty industry like cement, steel, or the chemical industry. So we are talking about 6 gigatons of carbon being needed by the end of the century to supply those sectors in form of energy, and about 1/10 of it still needed for the chemical sector in order to provide all the plastic that we have. This amount is similar to the amount that we are using today, and we could imagine still not needing more carbon, as we would recycling much more of our chemicals and will not need much more of the fresh carbon influx into the economy. So we will still need quite a bit of carbon. And this carbon needs to be renewable to be really neutral into the CO2 balance of the atmosphere. Biomass could be a good feedstock for it. Biomass will have captured the CO2 from the atmosphere and could supply it to our product. The typical issues that are mentioned on the use of the biomass is about sustainability and abundance. So what about those issues? If we look at the sustainability, we have a biomass that is needed for more important purpose, like feeding people, but we have also quite a bit of the biomass that is available as a byproduct of the rest of the industry. Residues coming from agriculture, residues coming from the forestry, once you grow crop or you grow timber, you grow wood for timbers, for instance, and those residues could be used for the industry. Mind you that we also have a starch which could be seen as a residue. Once you have enough starch for the food, you may still want to have more protein to supplement the food, and with those protein will come quite a bit of starch. So this excess of starch could be also used for making chemicals and making fuel. This is about the unavoidable byproduct of the biomass. But we also have the possibility to grow and harvest biomass that is sustainable in that it has a low input in form of low irrigation water, low fertilizers, pesticides, etc. Those will typically be multi-year crops, perennial or energy crops. So you have here a couple of options, and I'm also only talking about land biomass. Alissa was mentioning aqueous biomass, which you could also use, probably at higher cost and a low intensity. But for the land biomass, we still already have quite some option that will be sustainable. But mind you, the sustainability is not only about which kind of biomass you use, but equally important is how you grow it and where you grow it. So we can't really make a call on biomass in a generic manner. We really need to look locally at a typical project, where you do it and how you will grow it and what you will use it for. So far for the sustainability. Now the important aspect of the biomass is abundance. Do we have enough of it? And if we look at inventory done by Slater a bit less than 10 years ago, looking at how far you could push the biomass growth and harvest onto the planet, we are growing today about 1.5 to 2 gigaton of carbon in biomass, which is about a third of what we use today and about a third of what we could need for the end of the century when we have grown electricity. But that is not the limit, because we can improve agriculture, we can improve forestry, we can recover degraded land and make them more fertile, we can change our diet, we can change utilization of our product, and all those options would allow us stepwise to increase the amount of biomass that is available, increase it eventually beyond the 2 gigaton, maybe to 5, 7, eventually beyond the 10 gigaton if we are really aggressive in our measures. So we have the possibility to have biomass playing a very important, significant role into providing the carbon that we need for our economy. But it's good to use biomass, but why not use CO2 directly, as Alissa and Jorge has mentioned? Why not do it directly, taking it from the atmosphere? Well, let's first realize that for the product we want to make, being fuels or being chemicals, the biomass is already today affordable, a fairly low cost, competitive with the fuel, much cheaper than chemicals that we are making, certainly if we start about the residual biomass. This could be replaced by CO2, but CO2 comes with its cost. And Alissa has mentioned an optimistic target for CO2 capture of $100 per ton. CO2 is not enough to make product. We also need hydrogen, as Alissa was mentioning. Now, if I take already optimistic scenarios of $2 to $3 per kilogram, still above the one that she was mentioning as a target, you will see that eventually the cost of CO2 and renewable hydrogen is much higher than the biomass that you have for comparable oxidation degree of the carbon. So biomass is eventually a much better starting point, certainly for today. CO2 coming from the atmosphere could be competitive once you can decrease the CO2 cost, the cost of capturing the CO2, but also reducing really significantly the cost of hydrogen in order to flatten that line. So eventually, CO2 will play an important role, but biomass is probably on the short term a much more affordable option. So much for the first part, which is about the why biomass, realizing that we will need product containing carbon, being hydrogen fuel and chemicals, and the biomass being renewable will have a AAA status in the form of being available, affordable, and acceptable. But let's look at now how we can convert it, how we can use it, and do we have technologies for it? If we look at the digestible biomass, the easy biomass, form of vegetable oils or sugar and starch, we have already technologies that allows to convert them into various products, being fuel and chemicals. And for illustration, you will have here a sugar that could be converted to a variety of products, either by fermentation in the red box, or by hydrogenation in the green box, or acid catalysis in the blue one. And all those intermediates can further be converted, upgraded to biochemical intermediates or fuel intermediates via a variety of chemistry. So you could see from the sugar, you can build a fruit tree of product eventually. Now, if we talk about the cellulosic and the more recalcitrant part of the biomass, indigestible biomass, we have much more challenges in developing technologies to convert it. And why so? Because this biomass is complex, as it contains several components, lignin, phenolic polymers, or cellulose and hemicellulose, which would be polysugars. Those are not only heterogeneous, but also rich in oxygen and high molecular weight. To make the product that we want, we need to crack them down to much lower molecular weight by a factor 100 or 1000. And we also need to remove quite a bit of the oxygen in order to have the suitable structure that we need. And that cracking in the oxygenation is costing us quite a lot of headaches in the transformation, the conversion. We have two major approaches to do that. One is using low-cost processes, fairly simple technologies to crack all the biomass at once into an oil, like pyrolysis or catalytic pyrolysis or hydropyrolysis, and then taking that oil and do some upgrading, deoxygenation to have a final fuel. The process is simple, but typically the yields are fairly low, and the products we are making are homogeneous and fairly low value in terms of fuel, typically pure hydrocarbons. Alternative is to take much more complex technology, but targeting much higher value product and targeting much higher yield, utilizing the chemical structure, utilizing the oxygen built into the biomass. Can be done by fractionation to separate the component, disentangle the component of the biomass, and then upgrading them specifically according to their own chemistry to have dedicated components at much higher yield. And I will not be able to dwell into the details of the technologies, although it is a fascinating field, but in view of the time, I will not do so. But maybe a last finishing touch on those steps that we have to involve in those processes, those that still needs to meet quite a number of criteria of performance in order to be affordable, to be industrially practical. We have here 4 of those typical performance that you can test at very early stage of the research. The one is certainly the selectivity, for which you could have a very quantitative factors that you can find in the literature. And the selectivity is just there to have good efficiency of your biomass. It is typically an expensive material, and you want to use this as much as you can, as well as you can. The other 3 factors are about the efficiency of the plant, making sure you have a simple and compact plant with as little steel as possible, to have the plant also affordable. So it is about high reactor productivity, to have a small reactor. It is about high product concentration or low distillation resistance, to make sure you are not pumping solvent around, that you are not facing really big challenges in recovering your desired product from the stream that you are processing. And when you look at those factors, and particularly the productivity and concentration here, on a typical value chain for lignocellulose to product, you will see that the first step, the processing of lignocellulose to sugars, will typically proceed at fairly modest concentrations, so we have a problem here, and thereby also a low reactor productivity. So those units in the front end of the process, those units will be big and costly. Once you have the sugar and you try to convert it into platform molecules, it's typically not much better. The sugar is really reactive, tend to form gums and to foil your system. So we are typically operating at really low concentration and also low reactor productivity. So that step will also be expensive. Once you get to those platform molecules, which are much more stable, you can distill them off, operate them in high concentration with high productivity. And once you are there, it is no major challenges. We have a number of chemistries that can do that at industrial scale and industrial performance. So you see here, not only you need to develop the archetype of your full process, but for each individual steps, you need to make sure that you are meeting industrial performance to be economically, to have an economic potential. And when this, let me try to close this short presentation by reminding you why we would need biomass to provide high-duty fuels and chemicals, and ensuring that your biomass is still AAA status, being available, affordable, and acceptable. And also reminding you that we have technologies for converting the biomass, certainly for the digestible one, but we have emerging technologies now for the more recalcitrant one, for the lignocellulose. You have to, in developing those technologies, to make sure that you meet the performance indicators that apply to the industry. And herewith, I thank you for your attention.
Muchísimas gracias, Dr. Lange, por esa presentación. Y llegamos al último.
Thank you very much, Dr. Lange, for that presentation. Now we have the final speaker before the debate. I would like to introduce Dr. Rosalind Rickaby from the Department of Earth Sciences at Oxford University, where she's Professor of Biochemistry. And throughout her career, Rosalind has been a pioneer in combining disciplines of biology and chemistry to address climate in historical periods and the future of phytoplankton. She's going to specifically talk about methods focused on the use of the oceans for capturing CO2 and associated aspects of the circular carbon economy. So I'd like to pass the floor to Rosalind.
Okay, good evening. Thank you very much for the opportunity to give this talk. It's a huge pleasure to do so and to have heard such fantastic talks this afternoon. I'm just checking that you can see my screen on presenter mode. Is that okay? Okay, fantastic. So we've heard a lot about artificial techniques, perhaps and developing really new technologies for absorbing CO2 out of the atmosphere. And I guess the emphasis on my presentation is rather more about how does the natural world work in terms of absorbing CO2, and in particular, how does the ocean work for absorbing CO2? It turns out that it's been a remarkable store for CO2. It's a variable store for CO2, and indeed it's one of our largest exchangeable reservoirs of CO2 on the surface of the planet. So it currently contains about 38,000 gigatons or billion tons of carbon dioxide down in the deep ocean. So that shows us, and what I'll show you is that the capacity of the ocean to absorb CO2 is huge, and we have knowledge about how we may manipulate it. But I guess that perhaps a key point that I want you to take away from this is that also that volume of carbon that's already stored there provides a bit of a risk. If we want to manipulate the ocean, could we somehow perturb that natural balance that has made the ocean such a good store of CO2? So we've heard this a number of times today. There was an agreement in Paris that we need to try and limit global warming to 1.5 degrees C in the future. How do we do that given our current trajectory of global emissions? Of course, we need to limit those, but there was fairly good consensus that even with the limitation of emissions, that in order to hit that 1.5 degrees C target, we're also going to need the removal of 100 to 1,000 gigatons of carbon dioxide over the 21st century. And that equates to a value of about 1 to 10 gigatons of carbon dioxide per year. So just try and get our mind into that, because I've tried to be a little bit quantitative here about whether we can achieve that through the oceans. So just let's look at the current balance, and this is some beautiful data which shows us where carbon dioxide has gone since we started really accelerating its burning during the Industrial Revolution. So you can see here this build-up of emissions, whereby a third of it has gone into the oceans. So the oceans have already taken up about 500 gigatons of CO2 from the atmosphere since we've been adding it to the atmosphere at a rate of about 9 gigatons of carbon dioxide per year. So we've already had an enormous sink of carbon dioxide, a third of those emissions. The other third goes into the terrestrial biosphere, and then a third is essentially building up in the atmosphere. So the oceans have already moderated the impact that we would have experienced from those emissions of CO2. And just to show let's go a little bit back into the history of the planet. And this is now looking at an ice core record, and we've already seen this before by Jorge. This is going back over 800,000 years or so, and we have these beautiful records of temperature recorded in isotopes in these beautiful ice cores that we're gathering from Antarctica. And within those ice cores are these tiny air bubbles, and these air bubbles capture ancient atmospheres and tell us exactly what happened to CO2 in the past. And we can see this breathing in and out of carbon dioxide, where we've got elevated levels during interglacial warm periods and depressed CO2 levels when we've got cooler periods. And the most obvious exchangeable reservoir that is big enough to account for this change, and indeed can exchange on the timescale of these thousands of years, is the ocean. So the ocean has already breathed in CO2 during these glacial periods and breathed it back out during the interglacial periods. But how much? Well, we know these CO2 variations are about 80 ppm or so. And so we can calculate immediately that tells us that the glacial ocean has stored at least 800 gigatons of carbon dioxide and exchanged it on these sorts of timescales. But not only that amount of CO2 from the atmosphere was stored in the ocean, we also know that the enormous ice sheets that were spreading across the northern hemisphere obliterated large quantity of terrestrial biomass. So the forests of those northern continents were replaced by ice. And so the ocean had to absorb a large amount of carbon from that reduced terrestrial biosphere. And indeed, it's estimated to be about 2,800 gigatons of carbon dioxide. So in total, this glacial ocean was able to store 3,600 gigatons of carbon dioxide on the timescale of about 50 kiloyears, so about 0.07 gigatons of carbon dioxide per year. So that just equates, if you remember, I talked about 1 to 10 gigatons of carbon dioxide per year we need as sequestration in the future. And certainly the capacity of the ocean is large enough to absorb that, but its natural rate of sequestration is very much slower. So we're about 100-fold slower than is ideally needed. But can we understand something of the mechanism by which we can manipulate the CO2? And again, the glacial ocean starts to give us some lessons here. And there have been a number of different models which have shown how we can sort of add up to this 80 ppm CO2 chain. And the various mechanisms that are suggested are the cooling or stratification, so changing the density of contrast between the surface waters and the deep waters, which enables CO2 to be better stored in the deep ocean. We know the ocean is limited in this nutrient iron. It's fantastically low in the ocean. And we think in the glacial times, greater winds were picking up dust and putting them into the ocean and fertilizing the productivity. And once you have productivity in those surface waters, it dies, it drops down into the deep ocean, and it takes that carbon with it and enhances what we call as the biological pump of carbon into the deep ocean. And so we think iron fertilization was a component of this glacial CO2 drawdown. I've mentioned the land carbon reduction. And perhaps the other big component here is this idea that as we reduce sea level, we lose the shelves where the coral reefs are growing today. We know they grow in these nice areas where we can snorkel, but if you drop sea level by 120 meters, as we did at the glacial time, we remove all that area where the coral reefs can grow, and that limestone is essentially added to the ocean, raising this term alkalinity or increasing the basicity of the ocean and helping the ocean absorb CO2. So these are the sorts of components that are thought to go into the kind of equation that helps us understand glacial CO2. And it's really the biology, the chemistry, and the physics of the ocean. So as I've mentioned, we've got the biological pump, the growth of these phytoplankton, and unlike the terrestrial biosphere where that carbon gets stored in situ, in the ocean, because the photosynthesis only takes place in that surface layer where the sunlight can penetrate, then all of that organic matter then drops down into the deep ocean, and it can be stored on the timescale of 100 years in mid-depth or 1,000 years, which is essentially the overturning timescale of the ocean, as if it reaches the greater depths than about 1,000 meters. So we can think to manipulating the biological productivity of that organic carbon, and that will help us absorb CO2 into the deep ocean. I've mentioned the chemistry, the addition of those coral reefs to the glacial ocean made the ocean become more basic. And because of the way CO2 speciates in the ocean, it exists as this CO2 bicarbonate and carbonate ion, and it's only the CO2 aqueous which exchanges with the atmosphere. So by raising the pH and turning more of that carbon into bicarbonate and carbonate ion, we reduce the amount in that CO2 aqueous form that can exchange with the atmosphere. And we do that by raising the alkalinity or the pH. And indeed, this is where we think about enhanced weathering, which will add alkalinity to the ocean, or indeed other alkalinity addition processes. We could also think to the physics. This is just here showing air-sea exchange of CO2 and which areas of the ocean are sources of CO2, net sources of CO2 to the atmosphere. So I've generally talked about the ocean being a sponge of CO2, but there are areas where we're mixing the deep ocean up to the surface, and that can bring that carbon dioxide back to the atmosphere and ultimately degas. And so those areas are in the equatorial Pacific and in the Southern Ocean where CO2 is being returned. But if we can increase the stratification, that physical divide almost of mixing, we can help keep CO2 into the deep ocean. And so this learning about the ocean has indeed informed the various mechanisms which are really on the table to try and think, how can we manipulate the ocean to help us store CO2? And so we've got various ideas of just taking terrestrial biomass, dumping it in the ocean, lovely term. We've got ideas of fertilizing the ocean with iron. I've talked about this essentially it rusts out of the ocean, so it's there in very tiny levels, but we can potentially add it in soluble form. Nitrate and phosphate, we'll of course know about these for fertilizers on land, and they work just in the same way in the ocean. Thinking about alkalinization, turning more of that CO2 into those permanently soluble forms of bicarbonate and carbonate. All sorts of ideas of blue carbon, so carbon that's already existing, particularly in the coastal ecosystem, in mangroves, in macroalgae, and can we help preserve that or even benefit it and accelerate the biomass fixing of that carbon? The physics, we've got ideas of pumping the deep ocean back up to the surface to bring nutrients up and fertilize plankton, or artificially downwelling those surface waters, which will take carbon dioxide with it into the ocean. So these ideas of manipulating the pumps within the ocean. And perhaps an intriguing idea is to take the fact that the ocean is such a big reservoir of carbon, and it's absorbed the carbon for us from the atmosphere. It's done all the tough bit of that direct air capture and all of these different processes where we can use different chemistries. But the ocean's done it, and can we actually just remove carbon from the ocean and therefore help it absorb more from the atmosphere? So these are all the sorts of processes that are in play. And there was this, as Alissa has mentioned, there's been this fantastic report from the National Academy of Sciences where they've tackled 6 of these different approaches and tried to judge them based on the degree of knowledge of them, the efficacy, how long that carbon is stored for, the scalability, the environmental risk, the co-benefits to the ecosystem, the cost, all of these ideas. And what we learn is that perhaps in first place, I've tried to put numerical values on these just to get an idea of which of these approaches is most technology ready. And we certainly know the most about ocean nutrients, so the addition of ocean nutrients to the ocean. And I guess the questionable part of that is this environmental risk. And I guess I would say that of these categories of judging of these different approaches, It's really the environmental risk which is the absolute red light to any particular technique. And so to me, the challenge of artificial up or down welling is that we know that it's going to have detrimental impacts on the ecosystem, and it grades very poorly on all of these other approaches. So perhaps we can start to be focusing efforts on the more viable approaches like seaweed carbon sequestration, and the preservation of current ecosystems is an absolute no-brainer. It's perhaps not as scalable, it's perhaps not as efficient, but the benefits all round are kind of unquestionable. So focusing efforts on marine protected areas and perhaps enhancing the coverage of those is a key priority. I guess just to sort of close down, I mentioned the challenge of environmental risks, and to me, this large reservoir of carbon and putting it at risk is not something that we want to do as humanity. And again, the past, I'm afraid I come from an earth sciences department, so we try and use always history to inform us. And when we look to the glacial ocean, where we were sequestering more carbon in the ocean, we can immediately see evidence for decreased oxygen. This is just wiggles showing how we've reconstructed the dissolved oxygen in the deep ocean. And the moment you start increasing the stratification of the ocean, you reduce its oxygenation with the atmosphere, and that can reduce the amount of oxygen that's already there just purely from the ventilation. And if you start accelerating the biological pump, you're creating more organic matter, which needs to be respired. And that has the impact also of declining oxygen. So again, this shows us perhaps a consequence of any of these artificial manipulations of the biological pump, which is that we increase respiration and we decrease oxygen at depth. There are additional things we can learn from the geological record, and indeed some laboratory experiments that we've been running in my lab, which is, let's think about the alkalinity enhancement. There are various ideas to accelerate weathering on land, which provides this basicity to the ocean, where we can potentially undo ocean acidification, enhance the storage of carbon. But one of the challenges there, of course, we've heard of ocean acidification being a risk to calcifiers. So by adding this alkalinity, we could potentially undo that. But the challenge, of course, then is that the calcifiers may increase their calcification in response to that addition of alkalinity, and so reduce the efficiency of it as a CO2 sequestration methodology. And indeed, that's something that in the glacial ocean, we believe these pelagic calcifiers, these beautiful foraminifera and coccolithophores, increase their calcification at that time, almost to compensate the loss of the coral reefs. And we have some laboratory manipulations, particularly now of coccolithophores, showing again that they do increase their calcification as we raise alkalinity. The other challenge is any enhanced weathering, for example, we're going to add a whole bunch of other elements. You know, we're accelerating this natural process, perhaps 100-fold above the rate at which it would occur. And so inevitably there would be the input of other elements, so things like chromium, nickel, vanadium are trace components in basalt, but once you start weathering them at speed, you will increase their fluxes, and of course that has the possibility of being toxic to the ecosystem there. Another interesting feature that's come out of some work by Nikki Gruber and thinking about modeling the future, but this is just a picture showing a transect through the ocean of where anthropogenic CO2 has already been accumulating. So these orange and hot patches are showing the ocean essentially taking up that additional CO2. And if we do in the future reach a net zero type of scenario, of course, the CO2 will re-equilibrate and come back out of the ocean. And so this is something that we have to consider in terms of sort of jam-packing CO2 into the ocean, that it will filter back out depending on the depth at which we're able to place it. And I guess the other challenge, so I've tried to highlight the challenges of these ocean manipulation techniques. And just recently, in the last few months, the UK government, Alissa was showing what the US government are doing. And the UK government have certainly been thinking about net zero and routes for the UK to reach that, and looking at what proportions of CO2 removals do we need from various techniques, so direct air capture, biomass energy and carbon capture and storage, and all afforestation, replanting trees, and projecting these going into the future. And what's interesting is that they don't highlight the ocean at all in these future scenarios for the UK. And so any country which is trying to make some policy decisions about its future net zero strategy will not include the ocean because they don't see that as part of their governance. And so there is, in the same way that Alissa was saying that we have this global challenge to sequester CO2, we also need to create a global governance structure by which we could think about using something, a global resource like the ocean, for that sequestration potential. So just to finish, I think to say, can we manipulate the ocean to absorb more CO2? I think the answer is a resounding yes. But these technologies are very much in their infancy. And I guess there is the challenge of field scale trials where we might disturb something to learn how the system works. And so that we're in this kind of situation of trying to understand what is the best technique, I think, to really try at scale. It's probable that we require a mosaic of different techniques. This is a classic sort of spreading of the risk and spreading of scalability. And I guess for me, it's great to have these various ways of considering different approaches, but perhaps we ought to weight some where we kind of say, okay, actually, this is just not going to work because of, for example, the environmental risk. And as an earth scientist, I remain cautious in our acceleration of any one natural technique by 10 to 100-fold in terms of unintended consequences. And I'll leave it there, and thank you very much for your attention. Yep.
Thank you so much, Ross, and to all the speakers. Muchas gracias a todos por vuestras presentaciones. I'm going to switch to English now for a short debate with all of you. Thank you so much for the varied information. So we don't have a lot of time, so I want to get going with some questions to get the debate going. So I'm going to start with you, Alissa, and going back to sort of the overall approaches that are out there. And I'm interested in your perspective on the role that we're going to see played in the next, hopefully, few years by either industries or individuals. So you mentioned in your talk, obviously, how industries are changing their practices and the technologies that we can use to directly capture from those high emitters. And I want to hear from you what's your perspective on the potential of that, and what are the next steps there to make that really achieve a bigger, more successful part of what we need to do. But I'm also interested in the techniques you mentioned that are more sort of mundane, more sort of that we all can apply. So you mentioned this filter for our furnaces, and how close are we to that, to having real solutions in our homes? And what is the role, do you think, that we are going to play as individuals as well? What's the balance there? Who is going to be necessary here to make the bigger difference, or is it both the industry and the individual?
Thank you for the great question, but it's a big question you ask. So as you can see, we have Jean-Paul from Shell here. And I think this area of climate change mitigation became really real to industry at this time. Of course, for government, but any of these, even circular economy or even CCS, you need to have 3 pillars, because such a large scale really changing every aspects of human lives and environment. So you need to have technology, which can be either fundamental all the way to commercialization ready, but you also need to have a market and you need to have a policy. And each side has to pull right amount to really create the space, in my opinion. And until now, when you really look at the energy sector, it was driven by large corporations only. And energy users like us, we really didn't have much choices where we are going, what energy resources and energy mix we're going to be using. But now with the renewable energy penetration or all the things we talked about, we can see how they will be implemented in the environment, or biomass incorporate into our chemical material cycle. All these things are something we can visualize and understand the impacts of it. I think the one part missing is that general public who's not in this technology development does not understand the scale. It's not something we can just increase with the number, because the scale of how much of these we need to implement quickly is very, very difficult. I think there are a lot of emerging technologies, and in the past, it took about 2 decades to commercialize. We call it technology readiness level from 1 through 9. And in academic research, we go maybe up to 2 or 3. Industry doesn't go below down to 6 or below, just because it's a high risk. So there's something called a valley of death in the middle, and it's really hard for us to cross that. And it gets even more complex if whatever we introduce as a new technology or new approaches impacts the environment. Because ocean-based solutions, we should definitely do it. I totally agree with Rose, but at the same time, we need to know what could be consequences. Understanding that holistically will let us plan better. I think a lot of these, we should include the public and wide range of stakeholders, including industry and academia, so that we can really talk about what could be implication, because there's short-term and long-term implication. I think a communication is a lot more active than past, which I really like that. And materials I was talking about, like a furnace filter, it's kind of nice because compared to point source capture, like the reactor looks like a huge building, you don't know what's going on inside. People can actually see, same as bioenergy, same as ocean-based solutions. I think having public and other stakeholders being able to see with their eyes, they can really make that much closer to their decision making. So I think that's why I really like those approaches. But it does not mean having everybody furnace filters in their building not gonna make a huge dent in climate change mitigation. We should do it all. But I think there's something unique about scientific communication by getting involved with this technology development. The material itself for direct air capture are there. The question is, do we have a renewable energy or carbon-free energy to drive this overall process? So, or the circular carbon economy is definitely limited by our technology development, but also limited by availability of low, affordable, renewable energy, as well as hydrogen for the future, as John Paul talked about.
Great, indeed. So, going a bit into Jean-Paul's talk then, and talking about new sources of energy. I mean, naively speaking, I think society has been hearing most about air travel as the major source of CO2, and yet, you know, we can't live without air travel. It's such a fundamental part of our society. So, can you tell us a little bit more about what you think is going to become of air travel? How can we think of an air travel that is more sustainable? What kind of sources of energy are we thinking about? What is your view on that?
It is also a good question, Erika. I think for air travel, we have different options for different parts of the air travel. There are attempts to do electrification, and that will be mainly for the taxiing in the airport for the small distance. But you can't do really long distance with it because of the weight that you have, the weight of the battery pack. So eventually, you need to have, for aviation, you need highly dense fuel, dense in terms of volume because the plane has limited size, and dense in form of weight because you need to lift the fuel to the air to 10 kilometers in the air. So density is really important. For the time being, we are looking at two major supply of energy for aviation. The one is hydrogen, and the other one is hydrocarbon. And those will need to be renewable hydrocarbons. For the hydrogen, the beauty is the weight. Really light fuel, but because it needs to be hydrogen, you need a heavy tank, and it takes still quite a bit of let's say, of volume. So people are looking at whether investing eventually the design of the plane, having the passengers in the wings and having the tanks of the hydrogen in the middle. So we should come to completely different design, maybe also different design of the airport when you get there, in order to connect the passengers to the plane. So that is one alley that is being explored. The other one is renewable fuel based on carbon. And you have the biocarbon or you have the CO2 carbon. Today, the biocarbon is the one that is being implemented because it is the least expensive one. It's still about 3-4 times the price of today's Kero. It will come from vegetable oils, and we know how to do the trick. But the volume, we don't have enough of the source to supply aviation for it, and that is not sustainable enough. So it's just a stepping stone to get the machinery going, but that won't be the solution. We'll need to go to different kind of biomass to have the volume that we need. But the longer term, we could imagine capturing the CO2 from the atmosphere, reducing it with hydrogen. And if we can't put the hydrogen as gas into the plane, we'll put it on the carbon, make hydrocarbon fuel, and have it into the plane as we do now. And that is technically possible. So we have done it in Amsterdam, demonstrate about 0.5 ton of fuel that has been into a plane. Technically feasible, but it is damn expensive. So we need quite some improvement in technology in CO2 capture and green hydrogen to be able to have that working.
Great. I love that we would sit on the wings on the plane. Jorge, I'm going over to you to talk a little bit more about this potential of new methods like artificial intelligence to design better materials. So in your view, I mean, what is the big bottleneck that AI is going to help us with here? Is it the actual finding of materials? Is it the optimization of that sort of capture and release problem that we have? Where do you see most potential in the next 2-3 years for artificial intelligence in the new materials?
Okay, so it's a good question. I think big data and artificial intelligence really have a huge potential for finding new material, for optimization. Alissa and Ross they were talking about really big impact. For instance, Ross, she was telling that eventually, she knows that there will be a benefit in increasing the pH of the ocean, but she doesn't know what will be the impact in the long term. I think this may eventually should take in consideration a huge number of parameters. So, and in this regard, I think artificial intelligence may help us. So, in order to know what are really the factors or how many, that I believe it will be huge number, and maybe they really make an impact on that. So, and then maybe we may feel really more secure when we try to apply the best approach and don't risk so much on the possible impact of this approach. So I think maybe you play on your screen, you make it really a mess, but nothing happens. It's just kind of bit by video game. So then and then when you really know how to play with that, then you go and make a test on the real thing. I think there are a lot of potential about that, I may say.
Thanks, Jorge. Yeah, I'm going to end a little bit the debate now with the last question for Ross. Thanks for that segue, Jorge. So, Ross, you mentioned obviously, your high sensitivity towards, the unintended consequences of some of these techniques, and I just want to hear a bit more about your view of, what are those things that we are looking at as potential consequences or negative effects of manipulating the ocean? What are you most worried about?
That's a great question. I guess what would I say? I'm most worried about the ecosystem. I think and the biota therein. I guess not a lot of people know it because they're so microscopic, but the algae in our ocean provide half of the oxygen in our atmosphere, as well as taking out a large amount of carbon from the atmosphere. So they're real controllers of our atmospheric composition. They then filter down into the larger ecosystem. We rely on fish for our nutrition in many places. We've got the coral reefs, which are a major, massive ecosystem, which support tourism, etc. And I guess there is just this risk that we're going to do something. I do think there are things that we can potentially de-risk. So this absorption, you know, my big fear of any kind of manipulation of the biological pump is this use of oxygen. But there are some deep areas of the ocean where oxygen is very low already. And if you could target those areas for burial of carbon, that would be a great thing to do. We've also got the potential, and you know, much of the deep ocean has got calcium carbonate sediments in it, and those calcium carbonate sediments will naturally react with a more acidic, let's say, solution. So if we could inject CO2 down at depth, they will over time neutralize the acidity. And so I think perhaps the key thing for the ocean is location. You know, as we tend to think about it as a single box, and you know, this is what's going to happen if we put that stuff in the box. But I think there are key areas, and perhaps indeed this is where Jorge's suggestion comes into play, of sort of using approaches to try and understand the regions where you can get the maximum impact on CO2 and minimum impact on ecosystem, perhaps balance. And I think I think it's got to be a regional approach to the ocean and trying to figure out those key areas. I think that's what I'd like to say.
Thank you so much. I want to thank you all again, and as well as our audience, of course, but especially the speakers. Going to switch back to Spanish now for the last.
I want to thank you all, the speakers and the audience. I want to thank you for being here and for presenting these magnificent presentations, Alissa, Ross, Jean-Paul and George, Jorge, and thank you to the Ramón Areces Foundation too. Thank you once again, and good evening to you all.